Welcome students, welcome to Physics World by Spark Sudhakar. Okay, today I am going to discuss one topic known as behavior of a progressive wave at the junction of two media. Okay, this is a very important topic from not only IIT JAM point of view, but from any physics exam point of view. This is a very crucial topic. We can apply this not only transverse waves on strings, right? It can be applied for sound waves going from one medium to another medium, or an electromagnetic wave going from one medium to another medium, or what you call a light wave going from one medium to another medium, or a current pulse or a voltage pulse going from one circuit to another circuit, like that. Mostly general discussion I am going to do. Okay, true for any wave phenomenon, let it be longitudinal or transverse or current pulses or voltage pulses or whatever it is. Okay, EM wave or light wave, whatever it is. Okay, right? Behavior of a progressive wave at junction of two media. Consider a string like this. Okay, right? Medium 1 at x equal to 0 onwards, there is another medium, second medium, right? Let us call it a second medium. Okay, this red line is a second medium, black line is first medium. Okay, whenever any wave goes from one medium to another medium, okay, right? What are the properties of a wave? A wave will have frequency, amplitude, okay, wavelength, intensity, like this. Okay, which of the property? Velocity, wave velocity. Okay, different waves travel with the different velocities in different medium. Okay, so what are the properties of a wave? Wave frequency, wave amplitude, okay, wavelength, velocity, intensity, etc. Right? Whenever any wave goes from one medium to another medium, which of the properties will change? Which of the properties will not change? Means, remember, a very important point. Right? Let it be any wave. Okay, whenever it goes from one medium to another medium, its intensity may change, its amplitude may increase or decrease, its wavelength may increase or decrease, velocity may increase or decrease, but it is frequency which will never change. Okay, so when a wave goes from one medium to another medium, see, sun is emitting some radiation, thermal radiation, visible light, solar radiation from 1000 angstroms to 1 crore angstroms. Okay, right? It is passing through the plasma phase of sun. Okay, and it is passing through vacuum. It is entering into Earth's magnetic field. After that, it enters into Earth's atmosphere. It passes through gases. It passes through clouds. Okay, right? Water vapor, etc. Which of the properties will not change? Frequency of the wave will never change. Remember. Okay, so if the frequency, angular frequency is omega here, angular frequency here also will be omega only. Okay, next one, right? Its wavelength may be lambda 1 here. Okay, its wavelength may be lambda 2 here. Okay, 2 pi by lambda, propagation constant, I'll call it as k1 here, propagation constant, k2 here. Okay, velocity of the wave will be v1 here, velocity of the wave will be v2 here. Okay, what are the relation between v1, v2, k1, k2, etc.? We have to see. Frequency will not change, remember, frequency will remain same. Let it go from any medium to any medium. Wave frequency will not change. Okay, right? Now, here, then let linear mass density be m1 here, mass per unit length of the string be m1 here, linear mass density be m2 here. And whenever a wave passes through some medium, okay, any medium, including vacuum, also offers some resistance for the flow of waves through it. Okay, right? Let the characteristic impedance of that medium be Z1 here. Let the characteristic impedance of the medium be Z2 here. Okay, Z1 is the impedance of this medium, Z2 is the impedance of that medium. Okay, M1 is linear mass density, that is mass per unit length of the string here, mass per unit length of the string there. Okay, velocity of the wave. Okay, let it be transverse, because we are talking about strings, transverse wave be v1. Okay, the velocity of the wave there is v2. Here wavelength is lambda 1. In that medium wavelength is lambda 2. That is 2 pi by lambda 1 is k1. 2 pi by lambda 2 is k2 there. Okay, but frequency remains same. Keep that in point. And the boundary or junction is at x equal to 0. Junction is at x equal to 0. Okay, right? Now consider a wave which is going like this. Okay, wave which is going like this in the positive x direction, a wave is propagating. I'll call that wave as incident wave. I'll call that incident wave. Okay, it goes up to the junction, right? Now what will happen? A part of the wave gets transmitted. Okay, a part of the wave gets transmitted like this. Remaining part of the wave gets reflected like this. Or it will be reflected like this. Okay, I'll call this as reflected wave, RW. This as my incident wave, IW. And this as my transmitted wave, TW, I'll call. Okay, transmitted wave may be there, may not be there. Reflected wave may be there, may not be there. We have to see, we are seeing the most general case. Okay, right? So transmitted wave will be propagating in the second medium along the positive x direction only. Okay, reflected wave will be propagating in the first medium along negative x direction. Incident wave will be propagating in medium 1 along positive x direction. Okay, whenever, what is the general wave equation, general instantaneous displacement of any wave, right? Y equal to, we can write it as A sine omega t minus kx. Okay, right? Y equal to A sine omega t minus kx or A cos omega t minus kx. Both sine and cosine are harmonic functions only. Okay. Right? What is omega? Omega is the angular frequency of the wave. Okay. K is the propagation constant, or if in vector forms, I'll call it as wave vector or propagation vector. Okay. K bar, we'll write it as K bar. K bar equal to K into K cap. K cap is unit vector in the direction of wave propagation. K equal to 2 pi by lambda. Okay, it is called wave constant or propagation constant. K bar is the direction of the wave, direction, unit vector in the direction of wave propagation. Okay. Right now, in this equation, let it be sine or cos. If the wave is traveling along positive x direction, we have to put minus sign here. A minus sign inside the brackets implies that the wave is propagating along positive direction. Okay, if it is x coordinate here, wave is propagating along positive x direction. If I write it as ky, okay, wave is propagating along positive y direction. If I write it as kz, wave is propagating along positive z direction. Okay. If there is plus sign inside the brackets, okay, the wave is propagating along the corresponding negative direction. Means if omega t plus kx is there, it is a wave which is propagating along negative x direction, minus of minus x kx. Or it can as well be like this also. A sine kx minus omega t. Whatever it is, omega t minus kx or kx minus omega t, it only represents the phase difference. Okay, minus sign inside the brackets of wave equation. Okay, wave of what you call solution indicates positive direction of motion is along positive direction, corresponding positive x direction. If there is a plus sign, the wave is moving along in negative x direction. Okay, if kz is there, the wave is propagating along z axis. Okay, kz minus omega t means positive z axis. Kz plus omega t means negative z axis, like that. Okay. So plus sign inside the brackets will give you the direction of propagation, right, along negative coordinate. Okay, minus sign inside the brackets will give you direction of propagation along positive coordinate. Okay, so right now here what do? I'll take y equal to, right, general expression is y equal to, right, a sine omega t minus kx, because I am taking the x-axis as my direction of propagation. Minus sign implies that wave is propagating along positive z direction, positive x direction. Okay. Now a is the amplitude of that wave. Okay, amplitude of the wave. Now when I am talking about incident wave, right, instantaneous displacement of the incident wave, ya equal to amplitude of the incident wave sine omega t minus in which medium the wave is propagating, a medium where the propagation constant is k1. So I write it as k1 into x. So this represents the instantaneous displacement of a wave of angular frequency omega traveling along positive x direction in a medium with propagation constant k1. Okay. Right? Similarly, for reflected wave, how do I write? Reflected wave is also propagating in first medium only, but it is moving in negative x direction. Okay, that is, okay, YR, instantaneous displacement of the reflected wave, right? YR equal to AR sine omega t. Okay, because reflected wave is traveling in negative x direction, means opposite direction to the incident wave, I'll put plus sign here, plus k1 into x, because reflected wave is also moving in medium 1 only. Okay, next one, the instantaneous displacement of the transmitted wave, I'll write it like this. Instantaneous displacement of the transmitted wave, yt equal to, right, at, amplitude of the transmitted wave, right, sine omega t, because frequency will not change when I go from one medium to another medium. Okay, transmitted wave is also propagating along positive x direction only, so I'll put minus sign here. But only thing is, the transmitted wave is going in a medium with the propagation constant k2, so I'll write it as minus k2x. These are the instantaneous displacements of incident wave, reflected wave, and transmitted wave respectively. Okay, transmitted waves respectively. Now, I'll apply boundary conditions. What are the boundary conditions? Means the conditions must be satisfied always. Okay, At a specific boundary, where is the junction? Junction is exactly present at x equal to 0. So the conditions where the median must satisfy at x equal to 0, I'll call it as boundary conditions. What are the boundary conditions? Okay, what are the boundary conditions means? It is like this. The resultant displacement due to the waves which is present on the left side of the junction must be equal to the resultant displacement of all the waves on the right side of the junction. Means at the junction, right? Total displacement due to left must be equal to total displacement due to right side waves. Okay, that is, means imagine the wave is like this. Okay, right? If it is not same, how do I write? Total displacement due to all the waves on left side. How many waves are there? Incident wave is there, reflected wave is there. Therefore, right, instantaneous displacement due to incident wave plus instantaneous displacement due to reflected wave at x equal to 0 must be equal to, right, the total. There is only one wave on the right side, that is transmitted wave. The instantaneous displacement due to transmitted wave is yt at x equal to 0. Okay, this condition is quite obvious. Why means, if that is not the case, left side displacement is different, right side displacement is different, means what does that mean? At any instant, right, there is no junction at all, right? It is like this. One wave is going, right side is like this. Suppose say left side is like this, right? There is no junction at all. There is no continuity in the medium. Okay, right? The medium is broken now. The junction is broken now because left side displacement is different from right side displacement. Okay, right? Or it can be like this also. It can be like this also, right? Due to left side, okay, incident and reflected wave, resultant displacement is here, and what you call right side displacement is like this, means what? There is no junction at all. Junction is broken, we say, right? The medium is continuous, junction is unbroken, means what should happen? Left side displacement must be equal to right side displacement at x equal to 0. The displacement due to all the waves on the left must be equal to displacement due to all the waves on the right. On the right, there is only one transmitted wave. On the left, there are two waves, incident and reflected waves. So, yi plus yr at x equal to 0 must be equal to yt at x equal to 0. Okay, dou y by dou x, right? Slope also should be same. Okay, next one, dou y by dou t. Velocity or junction also should be same, because at the junction, right, the wave cannot have two different velocities at x equal to 0. Okay, at the junction, velocity, right, should be same on the left side and right side. Next one, the next boundary condition is like this. Okay, the transverse displacement on the left side must be equal to transverse, the transverse component of tension in the string. That is, right, the restoring force on the left side of the wave must be equal to the restoring force on the right side of the medium. Okay, right side of the junction. That is minus t dou y by dou x. Okay, at x equal to 0, right, on LHS must be equal to that on RHS. Minus t dou y by dou x at x equal to 0. But on LHS we have two waves. Okay, one is reflected wave, other one is incident wave. That is minus t dou y I by dou x at x equal to 0, right? Minus t dou y r by dou x at x equal to 0 must be equal to minus t dou y t by dou x at x equal to 0. This is second boundary condition. Why? When I am sending one transverse wave, right, suppose say that the string is an instantaneous displaced string is like this. So tension is here, this is angle theta, say. Okay, this becomes t cos theta, horizontal component. This becomes t sin theta. Okay, transverse component of the tension in the string is t sin theta. Right, when the force amplitude, when I am in order to create a transverse wave, I am applying some force. Okay, F like this. Okay, so that should be equal to minus t sin theta. Okay, right, minus t sin theta for continuous sake. When theta is very small, sin theta can be taken as tan theta. Okay, tan theta is nothing but dou over dou x, that is dou yi by dou x at x equal to 0, dou yr by dou x at x equal to 0. When theta is very small, sin theta can be taken as tan theta. Okay, tan theta is nothing but dou over dou x. Means this is the first boundary condition, this is the second boundary condition. I'll apply these first and second boundary conditions Okay, right? Also yi plus yr at x equal to 0 must be equal to yt at x equal to 0, dou y dou x. Okay, dou yi y dou x at x equal to 0 plus dou yr y dou x at x equal to 0 must be equal to dou yt y dou x at x equal to 0. Okay, right? Applying the boundary conditions, simplifying, I will define two parameters. Amplitude reflection coefficient and amplitude transmission coefficient. What fraction of the wave is getting reflected, what fraction of the wave is getting transmitted, we'll see. Okay, so I'll define amplitude reflection coefficient RA as equal to, right, amplitude of the reflected wave by amplitude of the incident wave. Okay, similarly, right, amplitude transmission coefficient TI equal to amplitude of the transmitted wave by amplitude of the incident wave. Okay, right? AI is amplitude of the incident wave, right? AT is amplitude of the transmitted wave. Similarly, what fraction got reflected? Suppose say there is one window over there. I'll throw 10 stones onto the window. Okay, 7 stones have passed through the window. 3 stones got reflected. What fraction got transmitted means what do we say? Right, 0.7% or 70% got transmitted. 0.3 or 30% got reflected. How did you get that 30%? Okay, thing which got reflected by incident. Incident is 10. Okay, reflected stones are 3. Okay, so 3 by 10, 0.3, you will say 30%. What fraction got transmitted? You will say 7.7 or 70%. How did you get that 70%? Number of stones which passed through the window, 7 by total number of stones incident, 10. 7 by 10, 3 by 10. Same is the case here also, RE and T. Right, so I'll substitute in terms of what you call those intrinsic impedance of the first medium, intrinsic impedance second medium. I'll get RE as Z1 minus Z2 by Z1 plus Z2, where Z1, Z2 are the intrinsic characteristic impedances of the first medium and second medium. Okay, right? Similarly, right, AT by TI equal to, I'll get 2Z1 by Z1 plus Z2. 2Z1 by Z1 plus Z2. Okay, this is the expression for remember. Very, very important from all exams point of view. Okay, because this is the most general case we are discussing, applicable for any wave in general, anywhere, in electronic circuit or electrical circuit or wherever it is. Okay, reflection coefficient, transmission coefficient. I'm not talking about in terms of energy, in terms of amplitude we are discussing. Okay, right? So Z1 minus Z2 by Z1 plus Z2 is 1 reflection coefficient. Okay, right? 2Z1 by Z1 plus Z2 is the transmission coefficient. Okay, now what is Z1? Z equal to, in general, characteristic impedance of any medium. Okay, Z equal to, right, MV, we write, or T by V, we write. T is tension in the string by V here. In the case of a wave transverse wave propagating along a string, the velocity of the transverse wave V equal to root 2 T by M, we write. M is mass per unit length of the string. T is tension in the string. Okay, right? So T by V will get T equal to MV square. MV square by V, nothing but MV. So Z equal to MV or T by V is known as characteristic impedance for which the string offers for the propagation of transverse waves through it. Okay, similarly, every medium for any wave propagation will offer some intrinsic impedance. Okay, in a lossless medium, the intrinsic impedance depends only on the elasticity and inertia properties of the medium. Okay, in a lossless medium where there are no dissipative forces, no dissipative factors. Okay, right? For a wave, an LM wave, what you call for an electromagnetic wave. Okay, in an LCR circuit, okay, root L by C, right? Similarly, here also, right? Impedance is M into V. That is electrical impedance. This one is mechanical impedance. That's all. We'll see one after the other. Okay, right? Z equal to MV equal to T by V. This is the definition of the characteristic impedance. Okay, now we will understand what fraction gets reflected, what fraction gets transmitted means. It depends on the relative values of Z1 and Z2. Okay, depending on the relative values of Z1 and Z2, right, RA and TA will be changing. Okay, now we have to see case one after the other, right? What are the cases possible here? Okay, what cases means it is like this. Okay, right, now first case 1, right, Z1 greater than Z2. So consider the case Z1 greater than Z2. When Z1 is greater than Z2, Z1 minus Z2 is positive. Okay, so RA is positive means what? AR is equal to something into AI. There is no minus sign. That means that reflected wave and incident wave will be in phase with each other. Reflected wave and incident wave will be in phase with each other. Okay. Right? And also transmitted wave. Transmitted, let Z1 be greater than Z2 or Z2 be greater than Z1. The denominator is always positive only. Okay, for Z1 greater than Z2 case, TA is positive, RA is also positive. That is, here in both cases, both RA and TA are positive. That means, implies what? Reflected wave and transmitted wave will be in phase. Will be in phase with incident wave. Will be in phase with incident wave. Okay. Right? When Z1 greater than Z2. Z1 greater than Z2 means what? The way we say light is going from denser medium to rarer medium. Okay, when light is going from denser, let any wave go from any medium to another medium. Part of it will get transmitted, a part of it will get reflected. Okay. When both what you call reflected wave and transmitted wave will be in phase with the incident wave, will be in phase with the incident wave when the wave is going from, say, denser medium to rarer medium or high impedance medium to low impedance medium, like that. Okay. Right? Next case, right? When Z1 is less than Z2. Okay, Z1 is less than Z2, that is case 2. Means here what is happening, wave is going from, say, rarer medium to denser medium or low impedance medium to high impedance medium. Okay. In that case, Z1 minus Z2 will be, right, negative term, means RA is negative. Okay, RA is negative means what? AR equal to, right, minus into something into AI. Okay, AR and AI will have one minus sign in between. It means that reflected wave will be with minus sign implies what? There will be a phase difference of 180 degrees or pi. So, reflected wave suffers a phase change of pi. Suffers a phase change. A phase change of pi with respect to incident wave. With respect to incident wave. Okay. What about TA? Right here, let Z1 be greater than Z2 or Z2 be greater than Z1. TA is always positive means what? Transmitted wave will always be in phase. Let the wave go from rarer medium to denser medium or denser medium to rarer medium. Transmitted wave will always be in phase with the incident wave. Keep that point in mind. Okay. Only the phase change will occur only for the reflected wave. That too, when the medium is going from rarer medium to, when the wave is going from rarer medium to denser medium, means if the reflection occurs at a denser medium, at the boundary of a denser medium, then what you call reflected wave suffers a phase change. If it is going from denser to rarer medium, means reflection occurs at the interface of a rarer medium, even reflected wave will be in phase with the incident wave. Okay, right? Transmitted wave is always in phase. Always in phase with incident wave. Okay. Only reflected wave suffers a phase change of pi with respect to the incident wave. Transmitted wave is always in phase with the incident wave. Okay. Right? This is the case of Z1 greater than Z2 and Z1 less than Z2. Okay. Now suppose say at the junction of two media, x equal to 0 is the interface or junction. Suppose say there is one rigid wall at x equal to 0. At x equal to 0, suppose there is rigid wall, means a string is tied to a wall and stretched under some tension T. Now I want to create a transverse wave, means what should I do? I have to keep on moving the string up and down like this. So a wave gets created, propagates with some velocity and goes up to the wall. Then do you expect the wall also to move up and down? No, isn't it? What will happen? The wave will simply get reflected. Means in this case, right, Z2, the impedance of the second medium, right, Z2 behaves as if it is infinity. Okay, means the second medium is of infinite impedance. It is not allowing any wave to enter into that medium at all. Okay, right? That is like a wall. That is like a wall. Okay, right? In this case, there won't be any transmitted wave. We can see now only reflected wave will be there. Means entire wave will get reflected. Entire wave will get reflected. Means it is like same first case only. Only thing is extremities of first case. Okay, the extreme case of the first case is what? the extreme case of case 2. Okay, Z1 is less than Z2, but here Z2 equal to infinity I am taking. Okay, second medium is not allowing any wave to enter into it. Okay, in that case, what will happen to REA? Just guess, what do you expect? Entire wave should get reflected. There should not be any transmitted wave. There should not be any transmitted wave. Okay, when Z2 equal to infinity, infinity plus something, infinity, something by infinity, 0, TA equal to 0. Means in this case, case 3, right, when Z2 equal to infinity case, Z2 equal to infinity case, what is happening to REA? I'll write REA like this, REA equal to Z1 by Z2 minus 1. I'll divide numerator and denominator with Z2. Okay, right, Z1 by Z2, right, plus 1 we get. Z2 equal to infinity here, right? So 0 minus 1 by 0 plus 1, it is nothing but minus 1. That is, right, AR by AI is equal to minus 1 means AR equal to, right, minus of AI means entire wave gets reflected. Only thing is reflected wave will suffer because of this minus sign. Reflected wave suffers a phase change of 180 degrees or pi with respect to the incident wave. Okay, transmitted wave, right, will be equal to 0. That is, TA will be equal to 0 here. TA equal to 0. Z2 equal to infinity. TA becomes 0. No transmitted wave at all. Okay, this is the extreme case of the second case. Okay, Z1 is less than Z2, but Z2 is infinity. Okay, next I'll go for the another extreme case of case 1. Right, Z1 is greater than Z2 means, right, this medium is a denser medium, this medium is a rarer medium, say high impedance medium, low impedance medium. Okay, Z1 is greater than Z2. Suppose Z2 equal to 0 means what? Suppose say the string is at x equal to 0, there is no further extension of this medium. Okay, string is not there. Simply you are creating one wave just like in a whip. Just like in a whip. What do we do? Whip means what? That long thing people used to use. Okay. Indiana Jones and the Riders of the Last Ark, the hero will carry one whip with him always. Okay, right? There is no other end. Okay, here when I shake my hand like this, a transverse wave gets created. It goes up to the end. Okay, there is no second medium at all. Okay, or Z2 is almost equal to 0. Say in that case, that is the next fourth case, extreme case of case 1. Okay, in the extreme case of case 1, what happens when Z2 equal to 0? Right, means the wave is going from denser to rarer only. So you expect that even reflected wave will be in phase with the incident wave. Put Z2 equal to 0 here, right? RA equal to 1, AR equal to, right, AI. There is no minus sign here. Means entire wave gets reflected. And one more interesting thing is what? Put Z2 equal to 0 here. 2 Z1 by Z1, TA equal to 2. That is, RA equal to 1 you are getting. Okay, RA equal to 1 you are getting when Z2, next fourth case, this one is when Z2 equal to 0, RA equal to 1 you are getting, right? TA equal to 2 you are getting. Okay, this is somewhat puzzling. Okay, when RA is 1, entire wave is reflected, what they expect transmitted wave should be 0, isn't it? Like in case Z2 equal to infinity case. Okay, but here I'm getting RA equal to 1, TA equal to 2. Generally, suppose if I throw 10 stones, right? Right, all stones got reflected means there should not be any what you call transmitted stone. Okay, I throw 10 stones onto a window, all 10 stones got reflected. That means RA equal to 1. Okay, all the reflected by transmitted incident is equal to 1. Transmitted should be 0. But here I am getting TA equal to 2. That is RA plus TA, right? RA plus TA is not equal to 1. Is not equal to 1. How do we understand this? Means we are talking about amplitudes. Remember, there is no amplitude conservation law. Okay, amplitude need not be conserved. Okay, right? Energy should be conserved, momentum should be conserved, etc. But no amplitude conservation law. We don't have anything like amplitude conservation law. If amplitude conservation law is there, right? Transistor amplifiers, etc., voltage amplifier, current amplifiers would have been impossible. Okay, right? So what is happening here? RA plus TA need not be equal to 1. RA plus TA need not be equal to 1. Okay. Now, we have seen 4 cases. That's right. Z1 greater than Z2. Okay. Right. And Z2 equal to 0. It's extreme case. Z1 less than Z2. And Z2 equal to infinity. It's extreme case. 4 cases we have seen. Right. Whenever the wave is getting reflected from a denser medium, reflected wave suffers a phase change of pi. Okay, when it is getting reflected from a rarer medium, reflected wave will also be in phase with the incident wave. But transmitted wave, let Z1 be greater than Z2 or Z2 be greater than Z1. transmitted wave is always in phase with the incident wave. These points you should remember in mind. Okay, right? But now here RA equal to 1 I got. Okay, earlier also, right? In this case also, how much have we got? RA equal to minus 1 I got. In the third case, Z2 equal to infinity. Right? In the first case, Z1 greater than Z2, RA equal to something into AI I got. Okay, ER equal to something into AI means RA is always present. RA is always present means reflected wave is present always in all cases. Let Z1 be greater than Z2, let Z2 equal to infinity, let Z2 equal to 0. Okay, Z1 less than Z2, whatever it is, reflected wave is always present. Okay, now in some cases, especially in some electronic circuits, when I want to send a signal from one stage amplifier to another stage, cascaded stage amplifiers. Okay, from first stage, I want 10,000 or 1 million times amplification. 0.1 microvolt should be amplified to 100 volts. Means, right, 10 to the power, what you call 7 times or 10 to the power 8 times amplification is required. In one stage, that much amplification factor will not be that much. Okay, so what do people do? They'll amplify it 100 times, 1 to 100. Okay, next 100 to 10,000, 10,000 to 10 lakhs, like that. In 3-4 different stages, they keep on amplifying. Means the signal has to be sent from one stage to other stage to other stage, like that. Now also, here also, see, I'm speaking into this microphone, right? Whatever my voice vibrations are, either this is a capacitive microphone or a resistive microphone, whatever it is, it will be converting that my audio signal into an electrical signal. That electrical signal goes through the wire, okay, to the amplifier. Amplifier amplifies that signal and feeds it to a speaker. Okay, we are hearing a loud voice. Okay, you are hearing a loud voice. Okay, my tone is getting amplified. Okay, right? Now, what happens when I'm speaking into this microphone, right? We are seeing that Z1 greater than Z2 or Z2 greater than Z1, there is always a reflected wave. Sometimes in public speaking, right, you'll see, you stand in front of the mic, you'll get that is a siren sound, sound will be coming. Okay, right? That sound is why, because of the feedback. Okay, so what if the electrician will come and adjust something? Right, whatever I'm speaking should go into the circuit without any reflection. Means I should not have any reflection. But in all these 4 cases, we are finding reflection. Okay, how to avoid reflection means the last and the most important case is, right, Z1 equal to Z2. We'll see what happens when Z1 is equal to Z2. Okay, when Z1 is equal to Z2, what will happen? Okay, Z1 equal to Z2. RA equal to AR by A. Z1 equal to Z2 means RA equal to 0. RA equal to 0, right, implies amplitude of the reflected wave will be equal to 0. And what about a transmitted wave Z2, right? Z1 equal to Z2 means, right, 2Z1 by 2Z1 you can take, right? TA is equal to 1. TA is equal to 1 means entire wave is getting transmitted without any reflection. This is, I think, right, in electron communication, this one is extremely important, right? There should not be the way the signal should get transmitted from one circuit to another circuit, from one stage to another stage without any reflection. Okay, that case, what do people do? The last and the most important case, 5th case is Z1 equal to Z2. Okay, means the both the stages should have similar impedances. When the impedance is same, okay, that's known as impedance matching. That is known as impedance matching. Okay, we can observe this impedance matching, right? When they are from the amplifier, right, we are giving it to the speaker. At the back of the speaker, there will be some 6 ohms or 8 ohms will be given. At the back of this amplifier also, right, it will be written like 4 ohms, 6 ohms, 8 ohms, like that. We will see what type of a speaker, what is the impedance of the speaker. If the input impedance of the speaker is 8 ohms, I should take the output impedance of the amplifier as 8 ohms only. Then only whatever is the amplified signal from the amplifier will be transmitted through the speaker. Otherwise, half of the wave or part of the wave gets reflected. Okay, right? This is known as impedance matching. Similarly, our internet connection also, that cable fellow will give connection to your TV. The output impedance of that cable must be equal to the input impedance of the TV. Okay, TVs are all, domestic TVs are all made throughout the world. There are only 2, right, input impedances possible, 50 ohms and 70 ohms. They'll fix something. Similarly, our internet connection also, that fellow will come, fiber cable will be inserted into your router. Okay, through router it comes into your computer. Okay, the input impedance of the computer must be equal to the output impedance of that cable. That's called impedance matching everywhere, right? That's why all devices throughout the world they are either made with 50 ohms impedance or 75 ohms impedance. Because it is my TV, my own company, I cannot make a TV with 120 ohms input impedance. Okay, because other cables will not match with me. Reflection will not, reflection will always be occurring. Okay, the signal will not smoothly pass from one stage to another stage. Okay, right. So this is known as impedance matching, right? That's what for common collector configuration is used in amplifier stage, buffer stage. Okay, for impedance matching only. So Z1 equal to Z2 case, only reflected wave will be equal to 0. Reflected wave will be equal to 0. Okay, right? So entire wave gets transmitted. But when I talk about amplitude, since there is no conservation law for amplitudes, right, I cannot make that whenever I say RA equal to 0, right, RA equal to 1, TA is not becoming 0, TA is becoming 2 in some cases. So there is some confusion. Means if this much amplitude got reflected, means how much amplitude got transmitted, I cannot know. Okay, I won't be knowing because there is no conservation law for amplitude, but there is conservation law for energy. Okay, there is conservation law for energy. I am giving 100 joules of incident waves energy. Okay, 60 joules of energy got transmitted, means obviously I know that 40 joules of energy must have got reflected. Okay, in terms of energy, it becomes convenient for us to discuss because once I know one coefficient, right, reflection coefficient, I will be knowing transmission coefficient. If I know transmission coefficient, I will be knowing reflection coefficient. Okay, right. So in terms of energy, what happens is we can take what you call instantaneous in general equal to half half ma square omega square, where m is mass per unit length, a is amplitude. Okay, omega square is the omega is angular frequency of the wave. Okay, right, this is the energy contained per unit length of the wave. Okay, right, what is energy with the energy propagating, that is the rate of propagation of energy, that power transmission is equal to half m a square omega square v, where v is the velocity with which that wave is propagating in that state. M into V, we have seen, right, nothing but our impedance. Okay, so incident wave is in what you call medium 1. So I can write the incident wave's power, what you call Pi equal to half Z1, right, omega AI, incident waves in amplitude AI square, omega square. Okay, similarly, reflected wave, right, half reflected wave is also in medium 1 only. So Z1 into, right, amplitude of the reflected wave whole square into omega square. Similarly, power transmitted is equal to half into transmitted wave in region 2, that is second region, second medium, whose impedance is Z2. Okay, so half Z2 into, right, AT square, amplitude of the transmitted wave into omega square. Omega square is common. Okay, right, so PR plus PI, and substitute this AR value, AT value, convert it in terms of EI, right, you will find that PR plus PT equal to PI. Okay, that means power reflected plus power transmitted is always equal to the power incident. Okay, conservation of energy principle. 100 watts of power is incident at the junction. 90 watts got transmitted, means 10 watts must have got reflected. That's it. Okay, that will get proven from this. Only thing is you have to substitute AR and AT values from that expression, right? AR by I equal to Z1 minus Z2 by Z1 plus Z2. Okay, similarly, AT equal to 2Z1 by Z1 plus Z2, right, into EI, substitute that value and simplify, you will get Pi equal to PR plus PT. From this expression, if I further simplify, I'll be getting the energy reflection coefficient and the energy transmission coefficient as like this. Okay, right, now instead of what you call RA and TA, I'll talk about RE and TE. Okay, energy reflection coefficient RE equal to Z1 minus Z2 whole square by, right, Z1 plus Z2 whole square. Okay, and energy transmission coefficient TE equal to, right, 4 Z1 Z2 by Z1 plus Z2 whole square, such that, right, RE plus TE RE plus TE is always equal to 1. Is always equal to 1. Okay, now there is no confusion here. Okay, right, RE plus TE must always be equal to 1. From conservation of energy principle, we will get the same thing. Okay, Z1 plus Z2 whole square by Z1 plus Z2 whole square. If you add these two, it is nothing but 1. Okay, so this is a very, very important topic from all exams point of view. Okay, in anywhere, in whenever a signal is going from one medium to another medium, we apply these principles only. Okay, let it be in electronics or electrical or what way, in EM waves, etc., etc., in optics, everywhere. Okay, now we can see the different forms. Okay, in terms of impedances I have given, in terms of velocities we can find out, in terms of linear mass densities we can find out, that is mass per unit length or mass per unit volume. Okay, in the case of light, right, in terms of refractive indices we can find out like that. Okay, now we'll see one after the other. Okay, any form may come in the exam. Okay, right, the questions may come in any form in the examination. Okay, right, now we have RA equal to amplitude reflection coefficient, RA equal to Z1 minus Z2 by Z1 plus Z2, and TA equal to, same is the case with what you call RE equal to Z1 minus Z2 whole square by Z1 plus Z2 whole square, 2 Z1 by Z1 plus Z2. These are the expressions for amplitude reflection coefficient and amplitude transmission coefficient. When the wave is going from first medium to second medium, if the wave is coming from second medium to first medium, okay, so suppose if the wave is coming from right to left like this, it will become, right, Z2 minus Z1 by Z1 plus Z2, and this becomes 2 Z2 by Z1 plus Z2. That's it, simply. Okay, if the wave is going from first medium to second medium along positive x direction, these are the expressions. If the wave is coming from second medium to the first medium, okay, from left, means from towards left, okay, it will be Z2 minus Z1 by Z1 plus Z2, and this becomes 2 Z2 by Z1 plus Z2. Remember it that way. Okay, here always the one which comes is what? The first one is from which medium it is going into which medium. That first medium's impedance will come in TA expression. Okay, first medium minus second medium property will come in the case of RA. Remember it that way. Okay, right, now Z equal to, we have in general written Z equal to T by V. In terms of velocity, what will happen? If the velocity of the wave in the first medium is V1, in the second medium it is V2. In terms of velocities, how do we write? Okay, so Z1 equal to, tension in the string will be same, isn't it? String will be, right, entire string, both the first string and the second string, right, will be in same time, will have same tension, isn't it? So I can write this as what? T by V1 minus T by V2 by T by V1 plus T by V2. Similarly, this is, right, 2T by V1 by T by V1 plus T by V2. If you simplify this, what do you get? Right, T gets cancelled. Okay, T gets cancelled here. So if you take LCM, it will be V2 minus V1 by, right, V1 plus V2. Similarly, this one will be 2V2 by, right, V1 plus V2, where V2 is velocity of the wave in the second medium, V1 is the velocity of the wave in the first medium. Okay, this is in terms of velocities, reflection, transmission coefficients. Energy coefficients will be similar, V2 minus V1 by V1 plus V2 whole square, and this is 2V1 V2 by V1 plus V2 whole square. That will not change. Okay, right, next, in terms of, in the case of optics, we will be talking mostly about refractive index. Okay, if a light wave of intensity I0 is going from a medium of refractive index N1 to a medium of refractive index N2. Okay, what is the intensity of the reflected wave? What is the intensity of the transmitted wave? If such questions come, it will be like this. Okay, right, now in general, what is expression for velocity? Right, what you call velocity of any wave equal to velocity of light in free space by, right, refractive index of the medium. What is general refractive index formula? Velocity of light in free space by velocity of light in the medium will give you refractive index V equal to C by N. C is constant here, so V2 can be written as what? C by N2. Okay, C by N2 minus C by N1 by C by N1 plus C by N2. Okay, this is also 2 into C by N2 by, right, C by N1 plus C by N2. We simplify this further, you will get, okay, similar to Z1 minus Z2 by Z1 plus Z2. Here you will be getting, right, N1 minus N2 by N1 plus N2. Okay, this one will be, right, 2N1 by N1 plus N2, where N1 and N2 are the refractive india of the first medium and second medium. Okay, what you call this is in terms of amplitudes only I'm talking. Intensities means what? Intensity means whole square. This one will be 2n1 n2 by n1 plus n2. Okay, in terms of intensity, if you talk, intensity means energy only. Okay, right? So n1 minus n2. So what is the intensity of the reflected wave? Intensity of the reflected wave, IR will be equal to simply I naught, intensity of the incident wave, into, right, n1 minus n2 by n1 plus n2 whole square. Intensity transmitted wave, we ask what happens, I naught into 2n1 n2 by n1 plus n2 whole square. Okay, 4n1 n2 by, right, n1 plus n2 whole square. Okay, in terms of refractive indices, in terms of velocities, questions will be coming like this. Okay, let it be any wave going from any medium to any other medium, depending on the properties of the medium, depending on the properties of this medium and that medium, we can calculate the reflection and transmission coefficients for normal incidence, of course. So okay, normal incidence, right? So this is one important aspect from what you call from any exam point of view. Just go through this video once again, make your own notes. Okay, and give me your feedback in terms of the comment section given below. Okay, thank you.